So over the next 50 minutes or so, we're going to try to look at how we can think of putting together a mission to look for traces of life on another body's surface. And we'll try to do it in a way that is as non-Earth-centric as possible and as pragmatic as possible. And what I mean with that is that we need to come up with something that we can implement on a space mission. Okay, so when people look at the origin of life, there's basically two ways to do it. You can go backwards, that is, you start from what you think you know about life on Earth. So, for example, you can use biochemistry and look at microorganisms. You can look at what chemistry can teach you. And since a few years, we have genetic analysis and metagenomics. And that will take you all the way to the last universal common ancestor, Luca. The other way is you can start to move forwards. And in that case, you begin with the origin of the terrestrial planets around our sun, and you use the laws of physics or chemistry to try to infer what the conditions and the processes may have been that shaped the origin of life. And somewhere in the middle, you have geology, which is the environment where organic chemistry and mineralogy shook hands for the first proto-organisms to occur. Now, if we go forwards and we look at the origin of the terrestrial planets around our sun, the first thing we have to say is that our solar system is very atypical. First of all, G-class stars like our sun are not the most common. And secondly, the fact that we have water in the terrestrial planets is exceptional. And that had to do with the inward motion of Jupiter and Saturn that were able to bring material from beyond the snow belt, rich in volatiles like methane, water, and ammonia, and then entered into a resonance and were ejected out to their present orbits and seeded the inner solar system with bodies rich in water, which then participated to the accretion process that gave rise to the terrestrial planets. Terrestrial planets, I mean Venus, Earth, and Mars. So the planetesimals formed by the gradual aggregation of small particles, but as soon as they grew in size to beyond a few tens of kilometers, they were able to gravitationally focus material, and the velocity of the impacts started to become higher and higher with the bigger the objects were, and so this released a lot of energy. So by the time that planetary embryos were formed, so we're talking a few hundreds of kilometers and larger, the impacts released so much energy that these bodies became giant balls of magma, and then differentiation could start. Even after the final process of formation of the terrestrial planets, meteoritic bombardment would have continued for a long, long time. So if you had been able to walk on the surface of the very young Earth, you wouldn't have been able to see anything. It would have been a surface covered by lava with a lot of water vapor that wouldn't have allowed you to see much, and bits of scum floating here and there. As the planets cooled down, the desolidification process went from the interior towards the outside, and the gases that were in solution in the magma bubbled out to create the first primordial atmospheres, which were supercritical, so with pressures of a few hundred bars, and composed mainly of CO2, nitrogen, and water vapor. And when those atmospheres started to cool down, as soon as they crossed the critical point for water, then the atmospheres were no longer able to hold all that water vapor as gas, and you had a process of condensation that it was a phase change. So it happened in a matter of a few days. Global oceans were rained onto the surface. So for many tens of millions of years, there were no emerged lands. It was just water, water everywhere. And the first bits of land that pierced the surface of the oceans were volcanic arcs, like the islands of Hawaii. It would have taken many tens of millions of years to start forming the first continental crust. So if we try to put all this story that I told you onto a graph, we can think of something like this. In the bottom, on the x-axis, you have the first billion years of the Earth. So we start from the beginning of planetary accretion. You see in red the magma ocean phase, then in light blue the part when we had the standing bodies of water. And this graph stops at 3.5 billion years ago, which is the oldest traces of life that everybody more or less agrees we can consider solid. So for Earth, from the moment when the ocean temperature became colder than, let's say, 70 degrees, you already had a window of opportunity for organic chemistry reactions and their products to become stable. And so we can think of this marking the onset of the period when conditions, we can call them compatible with the origin of life. And that is signaled by that blue bar that you see at the top, which for the Earth extends all the way to the right. One thing that is very, very, very important is in the beginning, the planets were hot. So there was a lot of volcanism, hydrothermal activity, and heat flowing from the inside to the surface. Now, if we look at Mars, however, the situation was different, because about 3.8, 3.9 billion years ago, there was a rapid change, and Mars lost most of its atmosphere, and the water that had been freely flowing on the surface went away as well. A lot of it is in the subsurface in the form of ice, but anything that was exposed on the surface basically either sublimated and then was lost to space. So if you want to look for traces of life on Mars, you see that there is the blue bar that you have to target is much, much smaller, because the chances for being able to find traces of possible microorganisms in the case of Mars is confined to the period between 4.4 and roughly 3.9 billion years ago. So now we have set the scene for when it is that we need to look for traces of life. Next, let's talk about what we're going to look for. So if you talk to people and you ask them for a definition of life, there are many, many floating around, but one that is elegant is that life is a self-sustained chemical system able to undergo Darwinian evolution. Now, this is an elegant definition, but it's useless. It's useless in the sense that we cannot put together a space mission to check for this. Evolution happens over thousands of generations, and to verify that there is an exchange of molecular information is complicated. But one thing we can do is try to look at what the people who try to synthesize life artificially in the laboratory use as a metric. And one of the things they always say is that the origin of life was not binary. It wasn't 0, 1. It wasn't that things were dead and then there was something that was alive. It is much more useful to understand life as a progressive acquisition of functionality, a stepwise trip from elements to a functioning system. And so a definition that I like for life is that it's a network of mutually supporting chemical reactions that includes a number of functions. And the key here is that these functions not only do what they have to do for themselves, but also help to catalyze processes on some of the other functions. So let's look at what those functions are. The first one is program. And it's the ability to have something in your life, in your living system, that it's a program that is stored chemically and that is able to inform and direct important chemical reactions in your system, like the formation of amino acids and then proteins. And this, the plan for making this is stored in molecules that we call genes. And in the transcription of this information, there can be corruption, and therefore some of these errors are passed on to the next generation, and therefore a system that has these properties is able to evolve by natural selection. So we say that there is an information polymer like DNA or RNA is able to catalyze important reactions, and to form these we need monomers, like for example amino acids to make proteins, and these monomers have to be sourced from simpler precursors, which the system would have had to take from the environment. The next important function is metabolism. And this is the ability to harvest free energy from the environment in order to perform functions like repair itself, and of course grow and reproduce. So in our case, we use a molecule called ATP, but simple organisms in general, they oxidize something. Like for example, here I'm indicating the oxidation of ferrous iron into ferric iron, but you could also oxidize organic molecules or sulfur or other things in order to gain that electron that you're going to use as energy currency to run reactions. And again, to form these molecules, you need precursors that you have to source from the environment. And the last function is containment. Containment is what you need in order to perdure both in space and time. It's something that allows you to concentrate regions and to keep away things that are poisonous to your system. And we do this with lipids in the cell membranes. And of course, they have to be sourced also from precursors from the environment. So we can now define our minimal system with this PMC, so program, metabolism, and containment. And it sort of looks like a cell in this diagram, but it doesn't have to be a cell. I'm just talking about functions, because this is what we're going to look for in another planet where we don't know what the chemistry of that life may be. Now, the environment may have played a very important role in forming this, and so we have to look at that as well. We need an environment that provides the ability to complexate, to progressively go further in creating complexity in organic chemistry. We need a proton gradient, and we need a flow of solvent. So in the case of complexation, what we need is the ability to confine, fixate, and enrich organic molecules. The proton gradient means a gradient in pH, typically is acidic out and alkaline in, and the flow is a mobile phase, typically of something liquid, that allows you to get rid of waste material. So we could posit that in the very beginning, the environment may have provided several of these functions. And one thing that we need is this. This is an experiment. You don't know if it's going to work or not. So you need an environment that is protected, in particular from UV radiation, that has a mild temperature excursions, and you want these to be ubiquitous. That means that it has to be repeated millions of times in different places, because you don't know which one of these experiments is going to work out. So for life to have appeared somewhere, we need this possibility to have existed for a few millions of years. And so I'll tell you again what they are. We need an UV protected environment, mild temperature, slow solvent flow, the ability to complexate organic chemistry. We need the environment to be repeated in many places and to be stable. We need organic precursors, and we need a proton gradient. So this intro is important because now we are in a position to try to understand where it is that we're going to look for life. So, could life have appeared in the early ocean? No. And the reason is, there are several, but the most important one is that you cannot progress and create more and more complex organic molecules in a diluted soup. Also, the top of the ocean is not protected against UV light, in particular high energy UV light. And remember that Earth didn't have oxygen until 2.5 billion years ago. What about a beach? A beach is nice because you have waves that wash over the sand or pebbles, and then as the water flows back, it acts like a bit like a chromatographic column. So you have the water and anything that's in it go through this stationary phase. Interesting, but again, is not UV protected, and you don't have the proton gradient to drive energetic reactions. What about hydrothermal systems that are exposed to the ambient, subaerial? Well, this is starting to look more interesting because you can have many of the ingredients. The one thing that is a bit problematic, particularly for the early Earth, when the sun 4 billion years ago produced much more UV light than it does today, and there was no ozone. So anything exposed on the surface would have been destroyed rather quickly. So that leaves us with the best possible candidate we have, which is submarine hydrothermal systems. How would have this worked? Well, in the early ocean, which would have been slightly acidic, you would have had water reacting with the ultramafic crust, and you can have serpentinization reactions, which is when, let's say, relatively low temperature water reacts with mantle minerals like peridotite to produce serpentinite, and in the process release hydrogen. This hydrogen then can react with CO2 through Fischer-Tropsch reactions, and you end up with an exhalation of very simple organic molecules like formaldehyde, methane, and other interesting things flowing through these chimneys, which are porous, and with a typical pore size of a few tens to hundreds of microns, where you have gradients in temperature going left or right of the main chimney. And you can think of the minerals, some of which would have had catalytic metals, forming a substrate onto which organic molecules can attach, and through all of this you have it's like a mini chemical reactor. So these are interesting micro environments that we can think of looking for in other places. So why do people care about Mars? Well, first of all, it is close to Earth. The second one is that we think that many of the processes that were important for the origin of life on Earth may have been active also on Mars. And finally, one other thing that is very, very interesting for us is that Mars doesn't have plate tectonics like Earth does. So the crust is not reprocessed every few 100,000 years. So on Mars is one of the few places in the solar system where we have access to material that is older than 4 billion years in age and has been on the surface for all that time waiting for us to study. So when we think about looking for life on another planet, and particularly on Mars, we have to think about a few keywords. The first one is habitability, which is the ensemble of conditions that make a certain environment hospitable to life. The other one that is very important is preservation. How do the biosignatures that we want to study make the trip in time from when those organisms existed? In the case of Mars, this could have been 4 billion years ago, until the present day. And this brings us to ExoMars. So it's a mission that we were ready to launch in 2022. We were going to launch with Russia, and when they invaded Ukraine, the European governments told us, you guys are not going anymore, so we had to stop 6 days before going to the launch site to start the launch campaign. We were ordered to stop. So the new plan is to launch in 2028 because we have to replace the Russian components with new European ones, and it takes time to build them. But anyways, I'll tell you where we are. We are trying to build a new lander, a European lander, but for the rest, everything else is ready to go. So this mission is about looking for the origin of life, and it has 3 great things going for it. The first one is that for the first time, we're going to look for organic molecules in the subsurface of Mars. And this is very important because if you think of Mars, it's like an ocean of pulverized material due to all that meteoritic bombardment, and this dust is everywhere. But you have the outcrops, the bits of indigenous rock that you can study with your orbiters. The problem with Mars is that the atmosphere is very thin. It's like the Earth's atmosphere at 30 kilometers altitude. And so we have 3 very important destructive agents that can get to the surface and even into the subsurface. In particular, we have UV light. Again, Mars doesn't have or has very little ozone. And so UV light is very strong, and the high energy part of the spectrum makes it to the surface just fine. Then we have UV photochemistry, like promotes the formation of some exotic oxidants, like perchlorates, for example, that when they get activated can oxidize and destroy the organic molecules that you'd like to study. And the final one is ionizing radiation, which acts like a million little knives. These high energy particles, they slowly cleave and cut away the functional groups of the molecular signatures that we would like to study. So the thesis of ExoMars, what we're doing that is different, is we're trying to collect samples from analysis from below this degradation horizon. Now, if you take a model organism like Escherichia coli, and you look at the the inventory of organic molecules, you find that about 80% of the inventory of organic molecules is in the cytoplasm in the forms of proteins, RNA, and DNA. Unfortunately, when the cell dies and these molecules are released into the geologic environment, they are quickly destroyed in a matter of days or a few tens of days. These molecules are gone. The molecules that do tend to persist in the geology for a long time are the armor of the cell, the lipids. And they make about 10 to 15% by weight. So let's look at what happens on Mars with organic molecules. So this is an equation that governs the radiolytic destruction of organic molecules. So you have the surviving fraction, which is the difference between what was there in the beginning and what is there when you go and study it. You have the radiolysis constant, which is different for every molecule, and you have depth. And until 2013, when Curiosity conducted the first measurement of ionizing radiation dose on the surface of Mars, we were using models, but now we can peg those models to a real value, and we can do some interesting experiments. So what you see in this graph, on the left, you have surviving fraction of organic molecules, and at bottom, you have depth under the surface. And what we've done here is we have exposed amino acids, a mixture of amino acids in a little glass ampule to accelerated gamma radiation bombardment to simulate ionizing radiation doses over 500 million, 1, 2, 3, and 4 billion years of exposure. So if we take, and we do it with amino acids because it's very interesting that Mars is a very cold place. As soon as you drill 50 centimeters below the surface, the average temperature is about 60 degrees below zero, because the average is the average between the day temperatures, which hover around 0 degrees, and night temperatures that go down to minus 100, 120. So if we take an Earth sample, let's say this one comes from Barberton in South Africa, and we look at the organics, it doesn't have a lot. It's about 10 to the minus 4 by weight in organics. And if we assume that all those organics are amino acids, which is not true, we can look at the graphs that you see there in the middle and ask ourselves, what is the maximum level of destruction I can sustain and still be able to make a good detection? Now, our instruments are able to detect with a sensitivity of 10 to the minus 9, so parts per billion. But to be able to say that we have made a good detection, we want to at least be able to have parts per million detections. That's 10 to the minus 6. So if I start with something that has 10 to the minus 4, the maximum I can sustain in terms of distraction is 10 to the minus 2, because 10 to the minus 4 times 10 to the minus 2 is 10 to the minus 6. So if you want to see how deep you have to go, what you need to do is navigate that purple curve and see where it cuts here, the horizontal line. And that, as you go down, tells you how deep you have to go. So if you want to be able to study material that is 4 billion years in age, we need to drill in the order of 1.5 to 2 meters. And this is another graph where I show you these are different amino acids exposed. All the curves correspond to 4 billion years. And what you can see is that the little guys survive better than the big molecules. And this is no surprise, because it's like the ionizing radiation is like a machine gun that is shooting bullets. And so if you are a big molecule, you present a larger target. So here is a little movie showing you what the Rosalind Franklin rover looks like inside. You have here at the back the service module with the computers, the batteries. In the front, you have the analytical laboratory. And at the very front of the rover, you have the drill, which is like a mini oil platform. It has 4 elements that you have to assemble in order to get all the way down to the 2 meters penetration. These at the back are the antennas of the ground penetrating radar. We're going to talk a bit about that in a second. These big surfaces at the front are radiators to get rid of heat. And you can see that the rover has solar panels. Let's look a bit at other aspects. So I told you that this mission has 3 good things going for it. So we talked about subsurface penetration, the drill, that is the first. The second one is the instruments we have in the payload. So it's very important for us to be able to have observations that are nested, because we go from the panoramic scale, let's say hundreds of meters after we land, and we have to go all the way to molecular scale. So we go through different instruments that observe at different scales. So if you look at the mast of a rover, we have a suite of cameras. We have 2 wide-angle cameras that you see here at the ends. They are like a 50-millimeter objective on a camera. They have more or less the same angular resolution as a human eye, and they allow us to take images in stereo. Then we have a high-resolution camera, which is like a 300-millimeter objective on a camera. And so here you see rectangles that show you what the wide-angle cameras see, and what the high-resolution camera sees. And co-registered with the high-resolution camera, we have an infrared spectrometer, because on Mars, everything looks brownish, and it's very useful to be able to learn about the bulk mineralogy of, for example, outcrops that you might be interested in visiting. So then you can figure out if you want to go to place A, B, or C. Drilling to 2 meters in depth takes us in the order of 4 to 5 days. So it's a big investment in terms of operational time. And so we have a ground penetrating radar, Wisdom, that gives us the stratigraphy under the rover with a resolution of roughly 3 centimeters. We get 3-dimensional maps of what lies under the rover down to a depth of roughly 5 meters. And this is very important because it's information we need in order to plan how deep we have to go to penetrate the sedimentary formation that we would like to obtain samples from. It also helps us to see if we have hard rocks like basalts in the way of the drill, and then we would just move and go somewhere else. Then at the base of the drill, we have an important instrument. It's CLUPI. It's a close-up imager. It has a resolution of 20 microns per pixel at the closest distance, but it can focus all the way to infinity. So at a meter distance, we have a resolution of 80 microns per pixel, and we can see far away. And it has a clever set of mirrors. By moving the drill, we can look in different directions. As I told you, the drill is a very complicated beast. It has a carousel with the various elements, but it also has an infrared spectrometer inside the drill tip that is able to see to the side through a sapphire window. It has an infrared lamp, and so as we go down the borehole or on the way up, we can obtain mineralogy information about what's on the walls in terms of rock composition. Here you see a little movie of Amalia. That's the name of the of the carbon copy of Rosalind that we have in the test center in Turin, in Italy. And here you see the drill obtaining a sample from a depth of 1.7 meters. It's accelerated, of course, because it moves very slowly. So the drill goes up and then rotates to provide a sample to this little hand that comes out from his window at the front of the rover. You see those brushes? They are used to ensure that the drill tip is kept clean. And now the drill is coming out and the sample is in that hole in the center. There is a piston that pushes it out and drops onto this spoon, and then it goes inside the rover to be analyzed. Now when this drill delivers a sample to the rover after it is ingested, the first thing we do early in the morning is we crush it. And then it's provided, it's put on a refillable container, looks like a little bathtub. And the first instrument that looks at it, it's called micro-omega. And micro-omega, it's a spectral camera. So every pixel in that picture, it's red, green, and blue plus 320 infrared spectral steps. So it's not really an image, it's what we call a hypercube. And then we have artificial intelligence in the rover that looks at every the absorption band in the infrared for every pixel, and is used to classify the mineralogy of the various grains. And then we can move the sample under the point and shoot instruments that use lasers. We have a Raman spectrometer also for mineralogy, and crucially, for the first time on a space mission, we have a UV laser for desorbing organic molecules. We also have 32 little ovens, like other missions have used, like the Viking landers or Curiosity, in order to extract organic molecules by pyrolysis, by heat. So this is what the refillable container looks like, and this is what a crushed sample looks like after it has been flattened. So we have this little highway in the center, and this is important because it shows how the sample moves when the carousel turns. So this is what the micro-omega hypercube footprint is like. And to give an idea, these are what Raman spots look like. And the Raman shoots on this highway in the center, and so does the laser desorption part of MOMA, the organics detection instrument. So if we have something that is nice, that lies outside this little highway in the center, only micro-omega can see it, as you see here. But for things that lie on this highway, we can train all three instruments to do mineral composition with Raman and infrared, and organic composition with laser desorption. Here I'm showing you the mass spectrometer of MOMA. This is an instrument, the size is the largest instrument that we have, is the size of a shoebox, and it cost us 130 million euros to build it. Here you see the UV laser. By the way, it's a joint venture between Germany, France, and the US, this instrument. So here you see the pulses of UV light last a billionth of a second. So they're so fast that the perchlorates don't have time to dissociate. And then the organic molecules are extracted, and there is a trigger valve that opens to ingest them into the ion trap, where they can then be detected. Once they are in the ion trap, we can get rid of the molecular weights that we don't want, and enrich in the ones we do want, and we can even do two-dimensional mass spectrometry. That is a secondary fragmentation of ions of interest in order to determine their structure. So here I'm showing an example of something that could have been a piece of a membrane. This is the other way we have of extracting organic molecules using the little ovens. There is a zirconium ball that presses the oven, and then the oven is heated up, and by heat, the gaseous organic molecules are desorbed. They go through a chromatographic column. In this case, I'm showing you how they are separated by molecular weight. So the little guys come marching out before the tall guys or the big guys, and then they're ionized with an electron gun, and they go into the ion trap mass spectrometer for detection. If you want to learn more about the mission and the instruments, you can look at this open access issue of Astrobiology. June, July 2017, we have a paper on the mission and a paper for each one of the instruments. So the analytical laboratory was put together under super ultra clean conditions, and it had to be assembled using this glove box train that you see on the back. It took 6 months for elements to make the trip through these cleaning stages. Every single nut, bolt, and little element has to be numbered, heat sterilized, and cleaned and assembled from the outside using those gloves. And then even in this part, which is not ultra clean, where everything has been assembled together, people have to dress up like astronauts in order to work on the clean parts of a rover. It takes about 3 hours to put on these suits and 3 hours to take them off. So this is what the analytical laboratory looks like with all 3 instruments inside: Micromega, RLS, and MOMA. And this is a little movie of the integration of the analytical laboratory within the body of the rover. This took place in Stevenage in the UK about 4 years ago. This is the inside, the part that is silver in color, that's the service module, and everything that is gold is the analytical laboratory. And here you see the first picture we took with PanCam, which is the white box at the top of the mast. On this picture, you see the rover on the right. It has been elevated in order to calibrate the ground penetrating radar. So there was a metallic target below the rover, and then we fired the radar to obtain readings. Here is the flight model of Rosalind Franklin being integrated onto the pallet. You see on the back to the left here, that's the back shell of the capsule. And the last thing I want to talk about that is key to the scientific success of his mission is a landing site. So it's on the Chryse Planitia, and what you see here in red are instances of clays. Now, this area is very, very old. It's the oldest site we could find on Mars. It's dated at 4.1 billion years in age, and it has had a complicated history. So what you see under 1 is the first interaction of water with a primordial crust that gave rise to these very large clay provinces, phyllosilicates in pink. But crucially, 3.9 billion years ago, there was a delta in this region because this is the outflow of the largest river system on Mars, which is Cogum Vallis. And for a delta to have formed there, this means that the deposits that were carried by the river had to have encountered a large body of water in order to precipitate and form the delta lobes. So this means that at the time, or right after the clays were formed, this area was submerged in roughly 10 to 100 meters of water. And because now we can see no obstacles between where we're landing on Oxyaplanum and the North Pole, the assumption is that the landing area is the coastal region of what would have been a very large ocean on ancient Mars. Lucky for us, about 2.5 billion years ago, it was covered by this dark layer of pyroclastic deposits that has protected what we are interested in studying from ionizing irradiation for a couple of billion years. So what it looks like today is complicated because a lot of these capping unit has been eroded by the wind, and so we have mainly clays everywhere, but exposures of delta fines and another interesting material. Of course, the thing that we would be most interested in looking at is if we can find hydrothermal systems. Now, the clays that we're seeing, they're very finely laminated. So you can think of them as like the rings on a tree, where every one of these layers records an instance of deposition and wetting. And what we have access to in this particular landing site in Oxyaplanum is a very basal part of the stack, the oldest clays. So this is very exciting because this is a time when if there was a chance for life to have appeared, it would have been more or less then. So here, I come back to the first graph I showed you at the beginning, and I have put the deposits that we have in Oxia in this temporal scale for you to see. And these are the dates of the landing sites that have been visited by the latest NASA missions. So Gale Crater by Curiosity, Jezero Crater by Perseverance. And you see that for the first time with Rosalind Franklin, we're really landing smack center on this blue period in the very early history of Mars. So a couple of few more pictures. This is the integration of the lander. This we'll have to do again, of course. This was the team right before we were packing everything up to go to Baikonur. And this is a final slide with a message that even though we have to wait a bit to launch ExoMars, we think that the science is too good. We will make a trip back in time to an epoch that has never been explored, neither on Earth or Mars. It's a unique landing site that preserves the most ancient example we have of interactions between water and crust. We will be the first ones to investigate Mars's third dimension, depth. We have a great payload to look for potential biomolecules, and we think that the mission will make fundamental discoveries in organic chemistry. And if we were to find traces of life, that would be so cool, so important, and will give such a boost to solar system exploration.